Hello and welcome to Tech Simplified TV. This is the 5th episode in VLSI Milestone series. A good functional MOSFET must have strict gate control over the channel region. We all know that although in smaller nodes, this control was becoming weak. At such a situation, a novel structured device having gate wrapped around three sides of the channel emerged and it became the savior. We call this device FinFET. In today's episode, we will talk about it. If you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, VLSI Milestone and FinFET. Next, leakage current and novel structures. Third, evolution of different multi-gate FET. Then what is FinFET? Different types of FinFET. Planar MOSFET versus FinFET. FDSOI MOSFET versus FinFET. Then bulk FinFET versus SOI FinFET. Next, FinFET fabrication flow. There are 2 slides on this topic. Next, performance parameter, corner effect. Advantages and disadvantages of FinFET technology. And finally, how FinFET got fitted in VLSI. Actually, in this slide, we will discuss the report card of FinFET, where it's used, which big houses are working with FinFET technology, and which are the technology node where FinFET is in production line. We are done with this slide. Now let's move to the first slide. VLSI Milestone and FinFET. This is the diagram we are referring for last few episodes. Milestone versus timeline and technology node diagram. So we are done with this SOI, green silicon, IK metal. Now we are here. That is FinFET. So FinFET technology, 14 nanometer, 10 nanometer, 7 nanometer and 5 nanometer, and the timeline is 2015, 2017, 2019 and 2020. Well, we all know that scaling degrades performance of deep submicron MOSFET devices. That's why these technology boosters like IK, green silicon, SOI substrate, that all has been introduced. Now VD controls the channel and VG losses control over channel. So this is the scenario of reduction of gate control. When device dimension is approaching lower node, it loses its electrostatic control over the channel region and control of VD become predominant. That is DIBL. We have already discussed in SOI episode. So VG is unable to shut off the channel completely in off mode of operation, which leads to an increased I-off between drain and source. Basic working principle of MOSFET, the channel must be created by the gate voltage, and with the use of drain voltage, there will be a constant flow of carriers from source to drain. By this way, the circuit will get completed. This is the basic principle of MOSFET. This happens ideally when source is quite far away from the drain. Potential at drain end is higher compared to source end. When drain voltage is applied, there is a field, so it has a area of impact for short channel devices. When source and drain are coming closer, that source junction, that area comes almost under control of the drain voltage. Like this. Here it's drain. From this actually controls this zone, and as a result, barrier gets lowered here. So VG is not really able to shut off the channel completely in off mode. That is, when VG is off, the channel is not off. Ideally, it should be when VG is on, channel is present. When VG is off, there should be no channel. That leads to increased I-off between drain and source. Now, multiple gate field effect transistor emerged as an alternative to planar MOSFET. Since one gate is not enough to control that off current and leakage, an idea of novel structure multi-gate field effect transistor emerged. MGFET demonstrate better control over channel and MOSFET performance. Among all MGFETs, FinFETs and Tri-Gate FET have emerged as most desirable alternative to MOSFET due to their simple structures and ease of fabrication. There are 2 forms of FinFET, double gate FinFET or triple gate FinFET. These have emerged as most desirable alternative to MOSFET because of their performance and ease of fabrication. So we are done with this slide. We will move to the next slide. Leakage current and novel structures. We know leakage current is one of the biggest problem of deep submicron and nanometric devices. As device dimension is reducing, leakage current is increasing. Channel is formed here close to this surface. Below that is a path for leakage current. So this area is not in control of this gate electrode anymore. This area contributes in leakage current. Gate cannot control leakage path far away from gate. So SOI MOS structure reduce leakage and chance of latch up. We have already discussed, since this area contributes in leakage, if we remove substrate here and replace that substrate with silicon dioxide, that is box layer, buried oxide layer, no current will flow from here. If we replace that substrate with silicon dioxide, there will be no available leak carrier and there will be no leakage current. We have already discussed about SOI devices, PDSOIs and FDSOI. Now these two types of SOI, in PDSOI this area is comparatively wider, and in FDSOI this zone is much narrower compared to PDSOI. A comparative study has been done in detail in SOI episode of this series. We know these SOI structures are good for controlling leakage and latch up, although they have their demerits like floating body effect, self-heating, all of these things. So here we will talk about only leakage. So this is basically advantage of SOI substrate. This leakage is occurring because of weak electrostatic control of gate terminal. This area is far away from reach of this gate voltage. By any means we can increase gate control, this leakage can be suppressed. From there, the idea of addition of another gate has evolved. Like addition of another gate can increase control over channel. So we can increase the control over this channel area by adding another gate. That becomes a DG, dual gate device. The main idea of a DG MOSFET is to control the silicon channel more efficiently compared to planar MOSFET. Silicon channel width is usually kept small and voltage is applied on both sides of channel. So the main idea of dual gate MOSFET is to control the silicon channel more efficiently compared to planar MOSFET, because there are two gates. If we call this one gate 1 and this is gate 2, if this zone is far away from gate 1, that is closer to gate 2, and this zone is far away from gate 2, it's closer to gate 1. So almost if we consider this total area, total width or thickness, the whole area is more or less in control of the two gates. So if we applied voltage in both the gates, the whole area in between is under control. Such a structure and operation effectively suppress short channel effects and leads to higher currents as compared with MOSFET having only one gate. Once we use both the gates, the whole region is closer to any one of the gate electrodes. So the whole channel zone is under gate control. We are done with this slide. Now we will move to the next slide. Evolution of different multi-gate FET. So first is planar MOSFET. Here all the MOSFET structure are shown without source and drain. The basic, this is planar MOSFET. This is ultra thin body or UTB planar MOSFET that is built on SOI wafer. And then comes double gate. Gate 1, Gate 2, this is the between silicon zone. Now FinFET. The structure of the FinFET is like that. It's on SOI and it's vertically standing position. This is cross section, so we cannot show where the source and drain here. Source and drain are perpendicular to this plane of the screen. In next slide, we will try to demonstrate a 3D structure. So then understanding will be easier. Now next is tri-gate. Here gate 1 gate, 2 gate. Just because distance from electrode, their oxide thickness is more, so effectively here it's 2 gate. Now here oxide thickness is uniform all around, it's tri-gate, considered as tri-gate. This is the difference. Now this is pi gate because of this structure, that is pi gate. Now this is gate all around. This is the silicon, then silicon dioxide, and then this gate, concentric circular cross section. Now this is omega gate. This is omega gate. Next, gate all around nanowire. Wider it's gate all around nanosheet FET. Now all these are different forms of multi-gate FET. As we can see from here, from FinFET, Tri-gate, all are, this gate zone is not on the basic wafer. It's vertically upward from the plane of wafer on Z axis. If that is plane of wafer, now this is vertically upward. That is Z direction, vertically. This is built on SOI wafer. It's a 3D structure. So we are done with this slide and we will move to the next slide. What is FinFET? Well, these are two FinFET structure. This FinFET is built on bulk and this FinFET is built on SOI. Here, as we can see, this is the basic plane. Suppose it's X, this direction is Y. So obviously, look, it's vertically. This red color is basically gate electrode. On the other side is source, here is drain. And the gate is covering it from all three sides. Here also the same thing. There is source on the other side, here is drain. So that is the channel length, and the channel is covered from all three sides with the gate. What is a FinFET? It's a multi-gate non-planar field effect transistor. Multi-gate, more than one gate, non-planar, because it's not on the same plane of the wafer field effect transistor. Channel is wrapped with gate from 2 or 3 sides. Due to the structure and operation, we consider it as double gate or triple gate. Like here, oxide thickness is more wide in this direction. So it's basically double gate. And here, this oxide is uniform on all sides. That is triple gate. So FinFET is fin-shaped FET. Fin is body part of fish which stick out of its body. A silicon film forms its body. This is the fin. Source, drain and gate, everything is within that. This silicon portion is coming out of the body of the wafer like this. Body of the wafer is like body of fish, and as fin come out from a fish's body, the fin is coming out from the wafer. So from there, from this structural similarity, the name derived, FinFET. And that fin is forms the body of the device. The channel of the FinFET is vertically positioned on the wafer plane. LG is gate length. This is the gate length. T silicon is fin thickness, and height of fin is H fin. So can be built over bulk silicon or SOI wafer. So basic wafer can be bulk wafer or SOI wafer. Now for double gate, with this 2 into H fin. For tri-gate, with this 2 into H fin plus E silicon. This is E silicon. This is thickness. And this is height. This is height of the fin, this thickness of the fin. For double gate, channel will be formed here in these two sides, and in tri-gate, channel will be formed in these sides. So we are done with this slide. We will move to the next slide. Now different types of FinFET. Because of gate design, we can say there are two types of FinFET. Double gate, triple gate. There is isolation oxide layer, this side and this side. If that is not uniform, so that is gate 1, gate 2 and gate 3. Now two types of gate connections. Shorted gate FinFET, independent gate FinFET. Shorted gate FinFET is 3-terminal device. Front and back gate are physically connected or shorted. Electrostatics of channel is controlled by both gates together. This is shorted. Source 1 terminal, drain another terminal, and gate another terminal. So 1, 2, 3. 3-terminal device. And the whole gate is shorted from this side to that side. And here is back gate and front gate, 2-terminal, source and drain. So it's a 4-terminal device. Gates are isolated. This side, from these two sides, different voltage can be applied to the gates. This flexibility is very useful. It's much more flexible. Here, gates are all shorted. We cannot operate them separately. That is SG FinFET. And here, IG FinFET, this back gate and front gate, we can apply different voltages there. They can be operated separately. So this is basically a 4-terminal device. Depending on wafer, there are two types. That is bulk FinFET and SOI FinFET. Bulk FinFET is silicon substrate, and on that this fin is built. And on SOI FinFET, this silicon substrate, then oxide. This oxide is buried oxide layer, and on that the fin is built. That is SOI FinFET. These are the classifications of FinFET. So we are done with this slide. We will move to the next slide. Planar MOSFET versus FinFET. So it's 2D structure. Gate is on that channel just below the gate, formed in the very same plane of the substrate. It's 2D structure. FinFET, it's not like that. This fin portion is vertically coming out from the surface of the substrate. It's 3D structure. Single gate, here double or triple gate. Cross section is also shown here. Now channel formed on silicon surface. Channel formed on perpendicular portion that stuck out of the surface. Here channel is formed in the very surface of the wafer. Here that fin portion is coming out of the device and channel is formed there. These are structural difference. Now leakage predominates in lower nodes of planar MOSFET. So channel forms on both sides or 3 sides depending on number of gate. Fabrication process is well optimized over multiple nodes. Planar MOSFET is obviously well optimized fabrication, and now number of gate is more than 1. So it has a better gate control, lower leakage. Although complicated fabrication if we compare to the planar FET. So we are done with this slide. We will move to the next slide. FDSOI versus FinFET. Here also 2D structure, undoped channel, single gate. Now FDSOI, in FDSOI also the channel is formed on the surface of the wafer. Here, a structure is stuck out from the wafer and channel is formed there. So it's 2D structure, it's a 3D structure. In FDSOI, the channel is undoped and gate is single. Here, depending on the structure, either 2 gates or 3 gates, and channel is doped. Channel formed on silicon surface. Here, channel forms in fin. Channel forms on 2 or 3 sides depending on number of gates. Here, 2 sides. Here, 3 sides. Single gate. Gate control is less compared to FinFET. Gate control better, leakage is lower. Fabrication process is less complicated. Complicated fabrication. FinFET is built either on bulk wafer, that is silicon wafer, or on SOI wafer. So SOI wafer fabrications are involved. Next on that, the device is formed. So initial wafer cost higher and wafer cost lower if we consider the bulk silicon wafer. If we consider SOI wafer, obviously cost is more. So reduce device variability as channel is undoped. And here device variability present due to fin doping and fin height variation. Reduce device variability. Variability is another issue. All devices are manufactured with some processes. Every process has some statistical deviation from its ideal situation. That deviation makes one device different from other device of very same run. Even within a die, one transistor differs from the other. So in FDSOI, since the channel is completely undoped, the variability due to doping is not present here. In case of FinFET, channel is doped, that variability is there. Another variability is fin height. Fin height is another point where variability is included. So variability plays a role in case of FinFET. These are the difference between FDSOI MOSFET and FinFET. We are done with this slide. We will move to the next slide. Bulk FinFET versus SOI FinFET. So these are the cross section. Fin is connected to the substrate through the oxide layer. There are oxide layer on both sides. It has lower manufacturing cost and the ability to be integrated with standard bulk CMOS technology. Fin is constructed on top of oxide, completely separated from the substrate. That is good from one point of view. That is one device is completely separated from the other. Isolation, good isolation is there. In case of SOI FinFET, insulator which isolates the transistor form the semiconductor's bulk. This is a SOI wafer. So this oxide layer is common with all devices and that actually separate one device from another. And insulator layer creates a defect which is called self-heating. Self-heating is a property of SOI because of the heat is generated cannot be dissipated through this substrate. So heat within the device increases when it's under operation. So here less back bias effect is here, good heat transfer rate due to substrate and good process compatibility. In case of bulk FinFET, the fabrication cost is less. So this is the comparison of these two types of FinFET. We are done with this slide. We will move to the next slide. Corner effect and process variations. About corner effect. The charge accumulation at corners or areas with higher curvature are higher. We know that from basic physics. This is diagram we have tried to show it. So here curvature is higher, so charge accumulation, and at the same time the field lines, electric field is higher where curvature is higher. In case of a conductor which has corners, so here curvature is obviously higher, so density of charge accumulation is higher in this area following this rule. So that happens with FinFET channel. This is called corner effect. So when a channel is turning on even at lower voltages compared to other part of the channel, electric field and accumulation of charge will be higher at these two corners, and here channel will form earlier compared to the other area. So that will be a premature inversion. The charge accumulation at corner or areas with higher curvature are higher. So electric field at corners are higher. Same rule follows for FinFET. Charge accumulation and electric field higher at corners. High channel doping create premature inversion at the corners due to charge accumulation. Electric field coupling in device corners results in lower threshold voltage of corner region. Corners are turned on earlier at lower gate voltages than the other parts of the channel. This doesn't exist in other parts of the silicon dioxide interface. This means that different regions of transistor with high electron density are activated at different gate voltages. This premature inversion at corners of triple gate FinFET degrades the subthreshold characteristic of FinFET, which results in higher off-state leakage. The corner effects must be suppressed to avoid leakage currents. There are various techniques available to eliminate the corner effect, such as reduction in doping concentration in channel and corner rounding, etc. If we do this curving, charge accumulation will be less, because with higher curvature, this charge accumulation will be higher. So by rounding off, if we can reduce the curvature, so that will be helpful. Another one is doping concentration reduction. Once we reduce the doping concentration, availability of free carriers will be less, so their accumulation will be less and this premature inversion decreased. Process variation. FinFET suffer from process variations due to small dimension and lithographic limitation. FinFETs are subjected to physical fluctuations like variation in gate length, pin thickness, gate oxide thickness, and gate underlap. Gate oxide is on the etched sidewall of fin and may suffer from non-uniformity. The degree of non-uniformity depends on lineage roughness of the fin. It's a hand-drawn schematic, right? When it's transferred on silicon, it will be something like this. Like I'm trying only like this. So on two sides, there is deviation. So that is lineage roughness. Line is not absolutely straight. Small deviation is there. So if that is the structure, it has some area. And now in reality, we are having a structure like this. Effective area under this is obviously not same accumulation of total charge, total current. That will be variable. Because of lineage roughness, we will not get a perfectly rectangle fin. Rather, this kind of a structure, and on that when oxide is deposited, that will also not be a uniform oxide structure. So these are the process variation a FinFET suffer from. We are done with this slide. We will move to the next slide. Now FinFET fabrication flow. So first, wafer preparation, and that includes cleaning of the wafer. Base is lightly p-doped substrate with a silicon nitride hard mask and a patterned resist layer on top. Silicon, this is hard mask silicon nitride. Resist layer is there. Now fin is etched. Highly anisotropic etch process is used. The etch process is time-based and there is no stop layer. In 22 nanometer process, the width of fins might be 10 to 15 nanometer, whereas height would must be twice of that or more. So this portion is etched in between. Finger-like fin structure formed. Now oxide deposition. To isolate fins from each other, oxide deposition is done. So these two fins are separated by an oxide layer. Now planarization. Planarization is to increase the smoothness or planarity of wafer through process like chemical mechanical polishing, that is CMP process. Now recess etch. Another etch process is needed to recess the oxide film to form a lateral isolation of the fins. We will recess from here. We will remove oxide. Keeping some, we will remove some oxide. We will see that step in next slide. These are the next steps. In last slide, we have talked about recess etching. By doing that, this area of this oxidation that is removed. Here oxide is removed and we get this structure. Now deposition of gate oxide. Now gate oxide is deposited on top of the fins by thermal oxidation to isolate the channel from gate electrode. On that, gate electrode will be formed in between, oxide gate formed here. Still the fins are connected. This fin and that fin are connected in between in substrate. A high dose angled implant at the base of the fin creates a dopant junction and completes the isolation. That is not illustrated here. Isolation is completed because this fin will form one device, this fin will form another device. So they cannot be connected from base. That will basically short it. So that's not desired to isolate one from another. High dose angled implant at the base is done. Here it's not shown. Now gate formation, a highly N+ doped polysilicon layer is deposited on top of the fins that is formed. Thus up to 3 gates are wrapped around the channel. 1, 2, 3. One on each side of the fin, and depending on the thickness of the gate oxide on top, a third gate. This is done on bulk silicon. If we follow the same thing on a SOI, since there is an oxide layer on SOI wafer, this oxide layer is already on the SOI wafer. Channels are isolated from each other anyway. In addition, the etch process of the fins is simplified as the process can be stopped on the oxide easily. In last slide, we said that anisotropic etching is completely time dependent, time set, because there is no stop layer. Here the buried oxide is basically stop layer that will get etched like this, and here this will form the fin. So this is the structure of SOI FinFET. We are done with this slide. We will move to the next slide. Now advantages and disadvantages. FinFET advantages: obviously better control over the channel, suppressed short channel effect, lower static leakage current, faster switching speed, higher drain current, more drive current per footprint, and now lower switching voltage, low power consumption. Gate control is better. We know gate is wrapped either from 2 sides or from 3 sides. In case of MOSFET, only we could use this part of the silicon. Here in FinFET, channel formed from 2 sides, and from tri-gate FinFET, channel formed from 3 sides. So effectively, with compared to the dimension, effectively channel is much more wider channel we are getting, right? More area is under gate control is as a channel. So lower static leakage current, leakage is less, faster switching speed, higher drain current. Parameter wise, its performance is really good compared to planar one. Now FinFET disadvantages: self-heating effect. Self-heating is even more predominant in case of SOI FinFET. Now quantized device weight. It's impossible to make fraction of the fins. There is always a ratio, whereby designers can only specify devices dimension in multiple of whole fin. Now higher parasitic due to 3D profile. Parasitic effects are there, very high capacitances, corner effect, and fabrication cost is higher because of this new structure, and more even with SOI wafer. So we are done with these advantages and disadvantages slide. We will move to the next slide. So how FinFET got fitted in VLSI. Big houses who work with FinFET technology: Global Foundry, Broadcom, UMC, Qualcomm, SMIC, Samsung, Intel, TSMC, MediaTek, ARM Holding PLC, Xilinx, Automera. All the big houses are working with FinFET technologies. And now application of FinFET: smartphone, computer and tablets, wearables, automotive, high-end network. Technology nodes, if we say that, introduced commercially in 2010 and became the dominant gate design at 14 nanometer, 10 nanometer, 7 nanometer process nodes. So we had all this about FinFET. So we are done with this slide and we are done with this discussion. So thank you for staying up to this point with us. Don't forget to like, share and subscribe. In case you have any question or query, please put it in the comment section. If you have any dislike, also put it in the comment section. Thank you and bye for today.